Now let's look at some basic vocab words. In the Bohr model of the hydrogen atom, which is the simplest atom because it has one proton and one electron, the lowest amount of energy that hydrogen's only electron can have corresponds to what we call the n equals 1 orbit. We call this the ground state. This is the lowest energy level an electron can have. When the atom gains energy, this electron leaps to a higher energy state. We call this an excited state. The atom is less stable in an excited state, so it will release that extra energy to return to its ground state, and it can do that all at once or in several steps. So here's the previous example we looked at an electron in a hydrogen atom receiving energy and going from the first energy level up to the third energy level. And we see here that it releases energy and goes from the third energy level to the second energy level. So it's releasing energy in steps. And when it absorbs energy, it absorbs electromagnetic radiation, and when it releases energy, it releases electromagnetic radiation. Now, what causes the energy levels to exist are the nucleus as well as the electrons. And every hydrogen atom has an identical nucleus, one proton, and the same number of electrons. So every hydrogen atom has the same energy levels available to it, and therefore can have the same energy transitions. The closer that these energy levels are to one another, the lower the energy of the photon emitted or absorbed. And remember, a photon is a particle of electromagnetic radiation. Lower energy photon means it's going to have a longer wavelength. And each element, has an emission spectrum or an absorption spectrum that is unique to that element. So let's take a look here at the hydrogen atom. If a hydrogen atom accepts enough energy to get its electron up to the third energy level, and that electron goes back down to the second energy level, the energy that is released in the form of a photon has wavelength of 657 nanometers, and it's in the red part of the visible light spectrum. If the electron has enough energy to be excited to the fourth energy level and then goes down to the second energy level, it releases a photon of higher energy than over here. These energy levels are farther apart, and the energy that is released is a photon whose wavelength is 486 nanometers, and blue-green light has a shorter wavelength and therefore higher energy than red. And if we have an electron that goes all the way up to the fifth energy level and then goes back down to the second energy level, these energy levels are even further apart, and so this photon has higher energy and a shorter wavelength. And every hydrogen atom is going to have the energy levels are going to be in the same place, and so when an electron goes from the fifth to the second energy level in any hydrogen atom, this is the photon that will be emitted, a photon whose wavelength is 434 nanometers. Or if an electron went from the second to the fifth energy level, this would be the photon that would be absorbed. Now, Bohr's model works excellently with hydrogen. However, it fails when it's applied to any other atom because all other atoms have more than one electron. Bohr's model cannot account for electron-electron interaction, which are very complicated. A better theory was needed to explain what's happening in an atom. And let me just say that when we are thinking about electronic transitions in any atom, we're still going to use this as our basis, but in terms of the mathematics that the Bohr theory used, it was not powerful enough to predict the behavior of other atoms. So Erwin Schrödinger used some high-level mathematics, including probability and the ideas of quantized energy, and He applied this to what are known as wave functions, and what he ended up with was a probability of finding an electron in a particular location of an atom. And to this day, this is still how we look at electrons in atoms, as probabilities. The vocab word orbital is an important vocab to know. This is a region where we have a very high probability of finding an electron in a given atom. And this probability is generally 90 to 95%. The other 10 to 5%, the electron could be any place. It could even be in the nucleus. So this idea of a probability of finding a piece of matter is not the way we look at our everyday life. If we leave something on a desk and nobody touches it, there's not a probability associated. That is where the pen stays. However, with an electron, because it is moving so incredibly quickly and it has such a small mass, the physics that relegate its behavior are very different than the physics that we use in our everyday life. So when we're talking about locations of electrons, we can never be 100% sure, and we always talk about them in terms of probabilities. So this is one important area where electrons are different than the matter that we deal with in our everyday life. Another aspect of electrons that is different from matter that we deal with in our everyday life is the fact that electrons have characteristics of both particles and waves. In fact, electrons have wavelengths of about the same length as X-rays. Now, you and I actually do have wavelengths associated with our pieces of matter as well, but our wavelengths are so incredibly small that their impact is minimal. But for electrons, their wavelengths are actually important. They're large enough to have an impact on their behaviors. So electrons, like electromagnetic radiation, have characteristics of both matter and of waves. This is what's known as wave-particle duality, and this is what's considered non-classical, because in the classical sense of understanding energy and matter, they are very, very different. But here we see that light has characteristics of waves and of matter, and electrons have characteristics of wave and matter. So both of these are actually have characteristics that are not so clear-cut from one another. Now, another important factor about the physics of an electron is it is impossible to predict the path of an electron in an atom. And so again, we can predict a probability, but we can't exactly know where it is or where it's going at any given time. So all these factors make the electron very, very different from the matter that we deal with in our everyday life, such as a pen or a baseball.